Good morning. Today we'll be learning about scalar and vector quantities. This is part 1 where we learn to represent vector quantities in directional components. And the second part will be calculation when vector quantities are in triangular forces, as in a system of a closed system. Okay, let's begin. So there's two types of quantities in physics. One is scalar, one is vector. Scalar quantities, as you might know, only have a magnitude and do not have a direction. For example, if I want to represent the speed of a car, speed is a scalar quantity, I can just give a magnitude and be done with it. Like, for example, a car is moving with speed 5 meters per second. However, if I want to represent that speed in vector, I will have to call it velocity. So, for example, if I want to say a car is moving with a velocity 5 meters per second, I also have to mention which direction. So, for example, a car is moving with a speed 5 meters per second towards the east. Examples of scalar quantities are speed, mass, density, pressure, work, and all forms of energy. Examples of vector quantities are force, weight, which is also a force, velocity, etc. Now, there's different ways of representing a vector quantity. This is the most handy one. So, let's say you want to represent a vector quantity on a diagram. So, 15 meters per second. In a direction, perhaps 30 degrees to the east. 30 degrees south of east. So you're first going to have to select a scale where, let's say, you say 1 centimeter represents 2 meters per second. And second, you're going to have to draw the diagram. So east, this is east, and this is south of east. So you're going to have to draw this 7.5 centimeters, and you're going to have to show this 30 degrees. You don't necessarily have to show the x and y, but I just did so that it helps in understanding. Now, the most important part of scalar and vector quantities is vector addition. So there's 4 methods of adding vectors. One of you don't really use the first one a lot in this A-level physics, but the second, third, and fourth are very useful. So the first, okay, before everything, you must always remember when you're adding vectors, you add head to tail. So let's say you're adding a vector, these two vectors, you must add the head of this vector to the tail of the next vector. Or for example, you have this vector. These are moving in 2 separate directions. What you have to do is move either one of them. So what I would do is extend this, because it's the same, it's moving in the same direction, and now it's head to tail. Pardon the drawing, it's head to tail, and then you can find the resultant. So the first method of finding or adding vectors is the parallelogram method, in which you draw a parallelogram and you solve it. So for example, in this one you don't really have to focus on doing the head to tail method, but which is why I don't use it very often. So let's say you have 2 vectors like this, okay, so 5 newtons and 10 newtons. Now, assuming this is a scale diagram, what you could do is the properties of a parallelogram. If this is 10 newtons, then when you extend this, this will also be 10 newtons. And when you extend this, this will also be 5 newtons. And when you measure this middle part, this will give you the resultant force. In this case, it will give you, I'm not really sure, but assuming that the resultant force, the calculations would be similar to this calc. So let's say this is 5 centimeters and this is 10 centimeters. This is 10 centimeters, this is 5 centimeters. And the angle between them is 30 degrees. Okay, this whole thing is 30 degrees. And if this whole thing is 30 degrees, this is also 30 degrees. So 30, 30. So you have 300 degrees left, because in a quadrilateral there's 360 degrees. 30, 30. This is 150, and this is also 150. So you know that this is 150. And then you can measure the length of this using a scale and then find the resultant force. And then you can give the direction using the angles that you have just shown. The second method of calculating vectors is the triangle method. This one is most used, and the triangle method is also, it goes hand in hand with the third method, which is the cosine rule to find the unknown side or angle of a triangle. So for example, you have this and you have this 5, 10 again, and this is right angles. So it's pretty simple mathematics to find the resultant force. You can just use the Pythagoras theorem and you can find the resultant force. Yeah, c squared is equal to a squared plus b squared. And in this case, c would be the resultant force, which is 11.2. Rounded to two significant figures. However, you don't always get perpendicular forces. What you could get is a force like this. Now, first you have to check if it's head to tail, and this is 5, and this is 10. First you have to check if this is head to tail, and yes, it is. And then you have to draw a resultant vector, like this. Oh, that looks nice. And usually they will give you an angle, or they will give you the length, and you have to find the angle. So in this case, let's say I've been given this supplementary angle, and I've been given that this is 150 degrees. So using the cosine rule, which I hope you all remember, if you don't, the cosine rule is, let's say this is r, so r square is equal to 5 square plus 10 square minus 2 into 5 into 10 into cos 150. So if you solve that, what you would get is that resultant is 14.5 newtons. In another case, let's say we're given that the resultant is 14.5 newtons. How would we find the angle between these two forces? Well, that's another formula, is cos theta would be this minus this and this. So 114.5 square minus, no wait, sorry, it would be the square of these two minus that. So 5 square plus 10 square minus 14.5 square, the whole thing divided by 2 into the two the forces at the lengths beside the angle, so 5 into 10. So you would get theta is equal to cos inverse minus 0.0 87, which would give you 150. I hope you understood. So that is the second and third, and it's most handy in my opinion. Please make sure that your forces are aligned head to tail. The third one, the fourth one, and this is also very useful, is the resolution of vectors. And if you take math mechanics, this is something that you will usually do in math mechanics. So, for example, this is the fourth one, resolution of forces. And what we do in resolution of forces is we resolve every force into horizontal and vertical components. So let's say, for example, we have a force of 10 newtons, 10 newtons, and we have a force of 5 newtons with a 30 degrees. Now this would be very easy to just resolve it into components, like bring the 5 newton here and minus 150, minus 180 minus 30 would give you 150, and then you can just use the method that I last showed you. But sometimes in questions, or some people even may prefer to use the resolution of forces. So at that case, you have no other choice but to resolve it into, you have no other choice but to resolve it. So what you do in resolution of forces is you firstly check which forces are in, what's that? Yeah, which forces are perfectly horizontal and vertical. So over here, 10 newtons is perfectly horizontal. So we just leave it as it is. And then we check if there's a perfect vertical. There's no perfect vertical. So now the things that are not perfect, you resolve into forces. So there's the 5 newtons. Okay, 5. And it makes a 30-degree angle with the x. Now you resolve this into two forces. So because it's acting at an angle 30 degrees from the x, there's a horizontal and a vertical component of this vector. So you have to resolve it. This is hypotenuse, adjacent, opposite. So the adjacent would be 5 cos 30 degrees, which would be 4.33, and the opposite would be 5 sine 30, which would be 2.5 newtons exactly. So now you have a horizontal force and a vertical force, and you see that the horizontal force acts in the same direction as the 10 newton force. So this is the opposite. So this is 2.5 upwards, and this is adjacent, 4.33. So what you do is you add the 4.33 to the 10, and you align this in head to tail fashion. So there's 10 plus 4.33, so you get 14.33, and you align this in 2.5. And now that there's only perfectly horizontal and vertical forces, you find the resultant. And resultant using Pythagoras theorem, which is, yeah, I hope you know the formula. And you would get that the resultant is 14.5 newtons. And there's one other important factor that you must take into consideration when adding vectors and subtracting vectors. That is, vectors have directions. So let's say, for example, there's a 5 Newton vector here, and there's a 2 Newton vector here. Please ignore the diagram. So when I tell you to add these, you notice that they're in separate directions. So when you add these, you just don't 5 plus 2 is equal to 7 newtons. No, that would be wrong. What you would do is, in physics, vector addition, that sign, i.e. positive or negative, represents the direction in which it is going. So let's say I take 5 newtons as positive, so this is on the right direction. The opposite direction is 2 newtons, which is on the left, so it would be minus. So when you're adding this, you would do 5 plus minus 2, and this represents direction, which would give you a resultant of 3 newtons to the right. Now let's say I am to say that 2 newtons is positive. 2 newtons is positive and 5 newtons is negative, as in I'm taking the left hand side as positive. So 2 plus minus 5, which would give me minus 3. What does that mean? Well, we took 5 newtons as negative, which is to the right. So because it's a negative answer, we know that the resultant is towards the negative direction, which is over here to the right. I hope you all understood. If you want to go through the forces in equilibrium and the triangle forces, check out part 2. Thank you for attending. I hope you all have a good day.